Just tell me when to start.
Yeah, you can go ahead.
All right, guys, welcome. Welcome to this recitation where we'll be just taking you through what we expect of you in homework 3 P1 and also homework 3 P2. I'll be starting you off with P1. I hope some of you have had time to look at it.
Sorry,
Yes.
Yes. Give us some time. There are some students in, so we need to connect, except they want to join from Zoom. We need to connect to the screen. Sorry.
Okay. Should I pause?
Yeah, just pause.
Okay.
Okay. Need to be connected.
I'm guessing we're ready to go. Hello?
Can you hear me? Hello?
Yes, I can hear you loud and clear.
Yeah, I think you can go ahead.
All right. Okay. All right. Welcome again, everyone. I was just saying that I'll be just taking you through the homework 3 P1, and then we'll have presentations from P2. There's a comment on the chat. Means no slideshow. I don't know what that means. Does it mean you want the slide? Oh, this one. I can see the slides.
Yeah.
But you are seeing it.
Yeah.
Let the others confirm if they can see from Zoom. Yes, I think.
Yeah, because I think just confirm others are able to see it and I'm able to see it on my end as well.
Okay, sure. Can the students see it right now?
Yeah.
Except, okay. Now,
Yeah. I can see.
can you see now?
Yeah.
Christine, you can go ahead.
All right. Okay, moving on. So we released the assignment and the early submission will be on Friday at 11:59. And then the final submission will be on March 28th. Just remember that there are no late days that can be used for P1, so please plan accordingly. And P2 it needs a more work, so just take your time to start early. We'll have two approaches, that is standard and autograd. And I have to say, with autograd, if you want to try out autograd, I would just request that you please have enough experience with it, maybe by starting with homework 1 or homework 2. Next slide. Next. So I'm just going to start you off with RNN. So like we learned in class that RNNs are essentially one block that is applied for every time step. They are used for sequence-to-sequence tasks where you have maybe a text that has that has a sequence time step 1, 2, 3, 4, or just something continuous. And from an RNN, we are able to take inputs from that particular time step and the previous hidden state to give an output. So what we are seeing here on the screen is, if unfolded, you'll find that we have different time steps. Maybe at xt minus 1 is the word that was before. I'm using words here because it's just what I will use as an example. And then xt can be the current token, and then xt plus 1 can be the next token. Next. So in RNN, it's very similar to what we were having in our linear layers, in that we were multiplying our inputs with our weights plus a bias, and then activating it to get some hidden state. Here we are just applying tanh function to a linear transformation of xt and ht minus 1. And ht minus 1 basically carries information from the former time sequences. Yeah. If I was in class, maybe I would ask who can tell me why really we use tanh. Basically, we use tanh because of it's unbounded. And the reason we use this is because tanh is nonlinear, and it's bounded between -1 and 1. I'm very sure you learned this in class. Unlike activation functions like ReLU or sigmoids, then due to this bound, we can mitigate the exploding gradient problem that we would face if the activation was unbounded like ReLU. And with sigmoid, we are more likely to run into vanishing gradients where the gradients are very small. So these tanh basically is centered around 0 from what you can see in our diagram. And centering makes optimization easy, since positive and negative values are also possible, and therefore allows easy gradient flow throughout the time sequences, and it reduces bias, and this helps converging become faster in training, because zero-centered outputs, they help prevent saturation in certain layers. Next. So for what we will be giving you really is phoneme. I would call this a many-to-one, in that the inputs are many, but we will expect one output, which it is essentially a few layers of RNN cells. We are taking different inputs, and at the final state, we will pass it through a linear layer to classify that a phoneme. So here we will have a bunch of RNN cells from H1, H2, and let's say T equal to 1, T equal to 20, equal to 3, so it can be easier. And then at the final layer, we would have a linear feed-forward for classification. Here, this RNN has 2 layers. So from the bottom one is the first layer, the second one, and RNNs basically can have layers that are stacked on top of each other, from what you saw in class. Next. So there are different types of RNNs. Basically, we have LSTMs, we have GRUs. I'm very sure you learned this in class, but particularly today, I want us to talk about GRUs, which you also implement for homework 1. In a standard RNN, we find that we face issues of long-term dependencies are not really kept well in a basic RNN. So when you have words that, if you are trying to look back at maybe 3 time steps or a few time steps, you're able to carry that information forward. But the main problems with RNNs is that they're not able to carry information back through a longer sequence of time. And one of the methods that was used to solve this was using LSTMs, because they were able to retain long-term memory. It's quite ironic because the name is a long short-term memory network, but this is because of the gates that they have. I'm very sure you learned this in class. In GRE, it's a special form of LSTM. It's a variant of LSTM. It has fewer parameters because instead of using 3 gates, it has 2 gates, that is the reset and update gate. And then it has a memory, content, and then from there, you can be able to get the hidden state. I'll tell you how it operates in the next few slides. And GREs are used for a number of tasks, such as, can be used for optical character recognition, can be used for speech recognitions, or any task that requires maybe long-term memory retention. But now that you have transformers, really, you learn later that they supersede the ability of GRUs. Remember that GRUs consist of 4 equations that represent the reset gate from what you're seeing, equation 1, the update gate, the memory content, and the hidden state. This section is the most time-consuming part of the homework because it involves a lot of derivatives. So it will take a bit of your time. Just know that the reset and update gates are very similar. So if you understand one, you'll basically be able to understand the other. Next slide. Is it the next slide? Yeah. So in the reset and update gate, we use the sigmoid as the activation function. The reason why we use a sigmoid activation function is because it's limited to the values between 0 and 1. And these values intuitively can describe how much information to pass to the next state. So if maybe the value is close to 0, we'd want to forget. And if the value is close to 1, we'd want to maybe remember. That's how I kind of intuitively interpret it. So in the reset gate, RT, it's made up of, you're able to combine, to have a linear combination of the input xt, you multiply it with the weight for that input and the bias, plus the hidden state of the previous layer, plus its own weight matrix, plus a bias for that part. So you kind of see from how we draw our RNNs in class, maybe the input comes from downwards and then the hidden state from your left. And then you combine that, and then you perform a sigmoid to have the output of your reset gate. And the reset gate basically determines how much of the previous state to ignore in computing the candidate hidden state, because it will be later used in equation 3. And then the update gate does basically the same thing. The only difference between these two is that we have different weights that are used to multiply the inputs and the hidden states. The reset gate has its own set of weights, and the update gate has its own set of weights. So the update gate determines how much of the previous hidden state to carry over, how much of information to carry over from the previous hidden state to the next hidden state. I'll explain how it happens in the next slide. So in the memory content mainly, which is the third one that has an input will be multiplied to a weight plus a bias, and then plus the highlighted element-wise multiplication of the reset gate and the a linear combination of the previous hidden state, it blends the new input with past information, and it is controlled by the reset gate RT. So the hidden state is it combines the previous states with the candidate states, and it is weighted by the that is in the last one, sorry. So in the memory content, it blends the new input with the past information. And we can see here at RT, it is controlled by the reset gate. So if the reset gate is closer to 1, you kind of remember a lot about the past. If it is close to 0, you'll not really remember. So I think we can go to the next slide. Right. Oh, did I explain about the update gate? Sorry, the update gate also controls how much of the candidate state is mixed into the new state. So if the update gate is closer to 1, the new state heavily relies on the previous hidden state. And if it's close to 0, it means the memory content has a large influence. So we are able to preserve memory over a long sequence of time. So from this, yeah. So from this, I think go back to the previous slide. I think you skipped one slide. Yeah, there's something I want to say about this. So to know that the RT or the reset gate is element-wise, we are able to multiply it with the linear combination of the previous hidden state. So in a sense, if you read deeply about LSTMs, it acts like a forget gate. When it's closer to 0, you're basically discarding information, and you're therefore like quote and unquote resetting your memory. So, and the hidden state is computed as a combination of the memory content NT and the previous hidden state, so that in case your update gate is maybe closer to 1, in this case, you will rely a lot on the previous hidden state. And if it's closer to 0, you will rely more on the memory. So in the last one, I would basically interpret it as this. If you're not relying on just the previous information you received, you're relying a lot on the past information, everything from the memory. But if you are relying a lot on the memory or things in the past a lot, you're not really relying on what you got in the present or in just the HT-1. That's just how I kind of interpret it. Now you can go to the next slide. Or maybe let me just pause there and ask whether we have any questions. Any questions?
No questions so far. Go ahead.
Oh, all right. So I will insist that because these are a lot of matrix multiplications and a lot of building up of layers. You have to learn how to calculate gradients correctly, and we provide you with the intermediate DWs and DBs. So you have the right ingredients for computing your DX and DH. We have a link here that has a document on how to compute derivatives. You may look at it and just say, I know all these things, but you will really need it because you'll have to really break down these equations into small parts if you want to solve them correctly. So I'll just urge you to just take a moment, just take a few hours and go through this document. It will be very easy for you to compute derivatives if you understand how to break them down into different parts. Like for example, in this equation where you have an element-wise multiplication combined with a dot product and an addition inside, and you want to even get you want to get the derivative of the function of x. It's easy if you just break it down into different parts and solve them one by one. Yeah. Next slide. So I would say, like, for example, if you have this equation where you have an elementwise multiplication of A and B, you know that these different colors influence each point in the in like, maybe let's say the addition of the green part of A and the green part of B produces the green part of C. So when you're doing the back propagation, you know that you're just supposed to do an elementwise derivative, all the way to A if you want to get to A. So once you go through the document, I'm a bit disappointed that I'm not there to show you, with hands. So please just join my office hour if you have a hard time with these chain rules. But just go through this document and you're going to really understand better about the difference of doing elementwise chain rule through elementwise multiplication and chain rule through matrix multiplication. Yeah, I'm not going to go through it in this recitation because it will need a deeper explanation, but just feel free to go through the document and come to my office hour in case any of you has a problem with that. Next slide. So we will also ask you to implement a GRU inference. So, it uses your implementation of the GRU described just now. And you will only be implementing a forward pass. So in this, it will be a many-to-many task. Many-to-many task means that many inputs are used to produce many outputs, basically. It can be in different variants, as you see in the diagram on your lower left. So it's different from your RNN phoneme classifier because your phoneme classifier was a many to one. Yeah, so we only needed one linear layer. But here we need to pass the hidden state at each time step to a linear layer. You have a linear layer at each time step to predict a character at each t instead of just the previous timestamps hidden states. So that is also something you're going to encounter in your homework one. I think I'm done, and Shita is going to take you through CTC. In case anyone has questions, I'll be here and you can type them on the chat or just ask. Thank you.
Okay, any questions for Christine? Okay, let's move on. This is the next part of the homework, that is connectionist temporal classification. So CTC is used to calculate loss when our input sequences and output labels have different lengths and no fixed alignment. So this method allows models to learn without needing pre-aligned data, which is crucial for applications like speech recognition and handwriting recognition. So for example, in this example, you can see that if the spoken phrase is hello, so the CTC allows the model to recognize it without knowing exactly which parts of the audio correspond to each letter. So instead, it learns using a probability-based alignment method that we'll see. So in homework 3P1, you have to implement these parts in the CTC directory. So first we extend the target with blanks, then we calculate forward and backward probabilities, and from that we determine the posterior probabilities, and finally we compute the CTC loss. So given an output sequence from an RNN or a GRU, we want to extend the target sequence with blanks, where blank has been defined in the initialization of CTC. So as shown in this diagram here, our target sequence is BEEF. And when applying the CTC rules, we will insert the blank tokens around each character. So our new extended target will become blank B, blank E, blank E, blank F, and a blank at the end. So this allows the model to predict each character over multiple time steps instead of focusing on strict alignments. Okay, so CTC also allows skip connection, which means that the model can directly move on from one character to another if needed. So in the figure, as you can see, the ones in this array indicate where the model is allowed to skip over a blank and go to the next character. Okay, so after extending the target with blanks, we move on to the second part, that is calculating the forward probabilities. So the forward and backward probabilities together allow us to compute the likelihood of the correct alignment and ensure that we account for all possible ways in which the input sequence could generate the target output sequence. So first, let's discuss the forward probabilities, which compute probabilities of this partial alignment from left to right. So as you can see is in this formula, the forward probability alpha at time step t and r is my symbol. So this is defined as the total probability of all paths starting at time step 0 and which align with the target symbol r up to SR at a time t. So this is from the homework write-up. This is a DP table where these columns represent time steps t equals 1 to t equals 6, and rows represent the extended target sequences. So each cell in this DP stores the probability of reaching that symbol at that time step. So let's take an example from this table. So at t equals 1, we start by initializing the probability of the first non-blank symbol that we have here, which is B, and others remain 0. Now at t equals 2, the probabilities start propagating forward, and influenced by previous values and the network predictions, we update the probabilities. So the code for this forward algorithm is given, would be given in the lecture slides. So please refer to that while implementing. After calculating the left to right forward probabilities, we introduce the backward algorithm. So this is just the reverse. We compute probabilities right to left. The backward probability beta t comma r represents the probability of generating the rest of the sequence starting from time t. So as you can see in this equation, this equation defines beta t comma r, that is the probability at time step t for symbol r. So it is basically summing over all possible future states, and each transition is weighted by the model's predicted probability. So why are these probabilities important? We want to determine how likely is it that a particular state can be reached from any future state. So which is essential for calculating the posterior probabilities. So again, the code for this would be provided in the lecture slides. So feel free to refer, and we'll also provide you with the pseudocode in our bootcamp material. So we calculated the forward and backward probabilities, and next we use them to calculate our posterior probabilities. This represents the probability of being in a particular state at a specific time when you are given the entire input sequence. So the posterior probability at time step t is calculated as the product of alpha and beta, and we normalize it by the total probability of all paths. So this posterior probability is used to compute the CTC loss by summing over all valid paths that lead to a correct output sequence. Any questions so far? Okay. Okay, so we extended the target sequence with blanks. We calculated forward probabilities, backward probabilities, and we used them to calculate the posterior probability. And now we use that to calculate our loss. So we can plug this gamma into our loss, which will ultimately be used to train our network. Okay, I think I'll update the loss formulation here. And yeah, the pseudocode for the loss computation would also be provided to you. I'll just update the formula here. And yeah, so that's all for CTC loss. And okay. So for CTC, after the CTC loss, we have a probability distribution over all the possible alignments, but it does not directly produce the final output sequence. So we need a decoding strategy to transform the model's output into a meaningful text. So we have two primary methods for this, greedy search and beam search. And we have asked you to implement both of these in the P1. Okay, so greedy search, like the name suggests, you can just decode the output by taking most probable outputs at each time step, providing the alignment with the highest probability. So as you can see in this example, we select the highest probability symbol at each time step to form the final sequence. So we end up with the word bat by choosing the top probabilities sequentially, as shown in the figure. And the final output would also require you to remove blanks and repetitions. So greedy search is pretty straightforward to implement, but it misses out on alignments that lead to outputs with higher probabilities later on. So for that, we introduce beam search, where we keep a beam of the top k subsequences at each time step, instead of just directly picking up the highest probability. So this is the pseudocode that we have provided in the write-up as well, but feel free to use any other implementation as per your choice. Okay, so this is a small example which demonstrates how exactly beam search works. So the leftmost node is the start of the sequence. At t equals 1, the model predicts possible characters, which is a blank A and B. Each has its own probability. And instead of picking up just one, just the most probable one, we define k as 3 here and always keep track of the top k subsequences at each time step. So each path has an associated probability. And at each time step, the probabilities multiply as new characters are appended. So, okay, so for example here, if A is selected at t equals 1, it can continue as AA or AB at t equals 2, each with updated probabilities, and the paths with the highest cumulative probability are kept in the beam. So here, after all the time steps, that is t equals 3, the path with the highest probability would be selected as the predicted transcription. So yeah, that's all you have to implement for CTC. Yeah, that's it.
We'll be taking you through the second part of the homework 3, and this homework was prepared by Ahmed Shubham, and we also appreciate those other TAs that have worked on this previous this homework the previous years. So just a bit of logistics. The early submission is due on March 14, 11:59. And you are submitting on Kaggle, in which we are measuring the Levitian distance, which should be less than 12 for your early submission. You have a Canvas quiz, which you have to complete, and the on-time submission will be on March 28. We are restricting you not to use attention for this homework because it will defeat the purpose of the homework. Also, we limit you to the number of parameters which you have to use. All of this is stated in the Piazza post where the homework was being announced. So let's go back to our homework one. Our homework one, part two. Basically, what we're doing is that we are giving you already processed audio signals in form of MFCCs, and these MFCCs were just being, you just built like a classification model to classify them based on the phonemes that you have, the transcripts of the MFCCs that you were given, which was fairly a basic task. And this time around, it will be something much more different than what you are seeing in homework one, part two. So what problem did we face with this type of just classifying phonemes or transcripts of when you are giving MLCCs, you classify them as a particular, that this is a transcript of this particular phoneme. The problem was that it was redundant. So when you are giving an MFCC or a sound signal, say yes. If I say yes, the moment I pull out my voice and I stretch out my voice, so I slow down, your predictions, if you apply that to what you have done in homework one, your predictions will be like, there will be a lot of repetition of Y and S and E's and all of that. So which is not, firstly, it's redundant. You have, it's not natural. Like that's not how humans maybe transcribe when they hear, say, an audio signal. And the most interesting thing about the first part of your homework was that it was time synchronous. So whenever you give an input as a speech, at each time step, the predictions for a transcript is being given out, regardless of whether you are saying a single word or you are saying a long sentence or you have spaces in between. You will always have predictions at each time steps for your transcript, which is not, as I explained, which is not natural, a natural way of predicting or transcribing from audio to transcript. So this time around, you'll be given utterance MFCCs as input, and we'll use a much more sequential way of modeling this problem in a way that we have a network which will get your input and then not just predicting transcripts at each time step, but predicting a transcript of the whole sequence that has been given, regardless of when it's received or is processed the transcript. So for example, if I said yes, like if we had done that in like using the approach we did in the first homework, you will have a prediction like this. So you have lots of Y's and E, H, and which is not supposed to be the case. Rather, if you use much more advanced or a sequential modeling, you have a prediction which looks like this. So this is basically the objective of this homework. So like I said, you still have the same features like that you had in your first homework, but this time around, it is not time synchronous. So your labels are order synchronous. What do I mean by this? So if I say big SHA, my prediction would be B would come first, SHA, SH will come later on. So in that order, I will not have SH coming before B. So that is for order synchronous. But time synchronous implies that at each time step I have, say, when I say B, it is being transcribed as B. When I say S, it's being transcribed as B as that particular time step. But in this case, the labels are not time synchronous. So I could say B now, and your transcription comes later on rather than the time I said it. So, and we'll also provide you with, you'll be using CTC lots as the first homework, as Tim has just explained to you. And it's fair enough that is implemented in PyTorch for you for this. You can have a link, click on that link to see if, to see the implementation of this loss function. And we'll be using this distance metric to calculate, which basically just calculates the distance between your prediction or your expected transcripts and the true transcript. So your predicted transcripts and the true transcript. So it calculates that distance. Also, the sequence of phonemes will, there are strings, and we calculate the distance based on the CMU dict and the CMU dict alphabet. This is all provided for you in the starter code we've given to you. So as you can see here, when you have like sequence of input, the predictions of your transcripts are somewhat not at the same time step as the input was being processed. So that is why we told you that this is the main difference between this homework and the first one you did earlier. All right, one more thing. We are giving you variable length input. So the first homework, we are giving you like fixed length input, but this time around we are giving you variable length. What do I mean by this? So your input was fixed length. They are being processed with regardless of like the size of the inputs, the size of the batches that you have been processed, but rather this time around we've given you, because this is a much more realistic way of like sequences are being processed, or the way you have sequences. Like if you say if you consider equal length, it means like you just have like a max length of, say, for a sentence that you have, you have a fixed length for all the sentences that your model will process, which is not what you see in reality. So in reality, you see much more variable length as your input. So, and in this case, how do we handle this type of variable length sequences? So the first thing we want to do is to do padding. So we pad the input that we have to have a fixed length. We determine the length of our padded sequences that we want, and then we process them. But there would come an issue if you're doing this, because if you have very long sequences, you might see that padding will, like it's an inefficient way of using your storage or your space that you have. So if you have two very long sequences, it will not be something great for you to just pad. So that's why we take you to packing. And packing essentially just arranges, sorts out the tensors in descending order based on the number of time steps in each sample, and then packs them together like this in a single tensor. So you have, you can see like the zeros, the item 3 here, you have 0 here, 0 for item 3, and they are all packed in here. So you have the yellow one here and the one here. So at the time step 0, you have all of these to be zeros, and then you pick all of these tensors or the sequences that you have here and pack them this way. This will be this will be very effective for like managing your space and your memory when you're processing this type of input. So so like I said, batch sequences, parts parts to equal length of batches, the packing, which you just arrange them in like descending order and put them in one tensor, and then for your effective use of space when you're doing the processes. But also you want to take note of like this is just like for for storing distance also input when you are loading your data. But when you are doing any processes, any operations on these tensors, you need to unpack them. So you'll be doing like padded sequence and then unpacking at some level when you need to do any operations on them. And I'll pull your attention to like the collate functions where I think you've used this in most of your data loaders that you can, it'll be very helpful for you to apply some of these processes in there, as well as doing your augmentations, uh, uh, time and frequency masking and other augmentations that you may use for this homework. So this is like a general ASR model setup that this looks scary, but it's quite simple. We'll try to explain, break it down to you. But basically, we'll have a sequential model structure to be in a way that we have an encoder that takes in your data or your MFCCs, whether packed or unpacked, whatever process you've done your pre-processing before. And then you have like a feature extraction layer that basically just extend the dimensions of your features. This is important because you might have an input that have like fewer dimensions and doesn't retain so much of context or meaning for that input that you have. So you want to expand your dimensions in a way that it has some semantic meaning of the input that it has. So you have an embedding layer or a feature extraction layer, followed by your sequential modeling structure or your LSTM or GRU or RNN, whichever you choose. And then when your features are being expanded like into a latent embedding or a much more important or feature carrying layer of your encoder, then you can pass that on to the decoder, which will basically be like a simple MLP that will constitute of like layers. And you also want you to go back to like, you can take a look at your homework. I think homework one part two and homework 2 part 2 as well. You had done something like building an MLP or a whole structure like a decoder based MLP. You can check that for your homework homework 1 part 2. So, and also in the decoder you have when you have like your final layer, you need to like convert it to probabilities. As the first homework team was explaining, we are doing decoding based on probabilities, like what is the most probable phoneme that or phoneme that your model will predict. So it's not just predicting based on like the time step that the signal was received, but it's predicting based on how probable it is. This will help to reduce that level of redundancy that we had faced earlier. And then we use like an external CTC decoding, which PyTorch has done a great job for us to implement. So yeah, just in addition to what I've explained, it's used to generate high-level representation. That's the encoder. and it has no labels when you are training. This is like in modern world, there are encoder only models that will focus just more on like expanding your input into higher dimensions, and then you can get even predictions from there. So this is very important. We advise you to use like you can use CNNs for your future extraction layer, and then build up with an RNN, and later on just pass them to your decoder. And it's trained jointly with the decoder. So the decoder takes in the feature representations from the encoder and tries to generate the closest match to the expected output. So you have your labels, which are the transcripts that you're looking at, but your model will predict some transcripts. So what you'll be trying to do is to match those predicted transcripts to or predicted phonemes to the ones to the labels that you have. And in that case, you have a loss function that you apply in order to 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 minimize it. So basically, as I said, also we can train like a decoder only model, maybe based that depends on like a pre-trained model, and then we use that as we have that feature extraction that is being done or transforming input into a latent space that is being done by the encoder completely wiped out, and like the decoder works only on its own. Yeah. And then we have also the embedding layer, as I explained. Basically, was we this is optional, by the way. So, but we recommend you to use it. Because if you focus just on the dimensions that we've given you, you might not get much from, like your decoder will not be able to do a great job at the level of predicting the phonemes as expected if the dimensions are lower, because it basically has less information about the input. So moving on, just talking about the embedding layer, you can decide to either decrease or increase the dimensions of your input. That's a decision you make. And take, for instance, an example like in MLP, you have 10K vocabulary representation of, say, of a particular word, and you want to say maintain that encoded word in like in numerical values. What you do is like you can create like a one hot encoding of that word that you have as an input, and then you pass it through your model. But this will be like if you have a long text, you have like very large vectors to deal with if you are doing like one hot encoding. So, but if you are using like an embedding layer, you can either decide to increase or reduce. In this case, we might decide to reduce this the size of for our tensor by decreasing it to some real value, and this is much more smaller to handle by your model. So like I explained earlier, you have your input dimensions to be 27, and this is basically the same like what we had given you in the first homework. So you expand this dimension to get much more information from the input. Consider, for instance, you have an input having three features. You have the features in one dimensions and the time steps in the other dimension. What your embedding layer, which is basically made up of like convolutional layers, what it will do is if in case you want to increase like the the dimensions of your input. You've done this, by the way, in homework 2, where like you try to expand, like you build like deeper networks, either expanding using like a hourglass or using a cylinder or whatever structure you use for your model. That is done like with your convolutional layer. So you can either decide like to expand the input based on that. And yeah, for instance, your kernel and your padding and stride will determine the values you have. They will determine if you want like your proceeding output, if it will be like a greater dimension or a lower dimension. And I think you've covered this in class, so I won't spend so much time on it. One more thing about your 1D convolution that you'll be doing in the embedding layer, you have to take note about the way PyTorch expects input for your 1D convolution. So you might have your input to be starting with like byte size, maximum length, and the number of features. But your PyTorch is expecting, say, number of channels, which is equivalent to your byte size, which is n in this case, in channels, which is like your number of channels, and then the length, which is like your features. So you might want to like do a permutation in order to put it in a structure that will be understandable by PyTorch. So you will be performing things like permuting the input to align with the dimension we see. So what this one basically does is it switches these dimensions from T to 27, as you can see here. So you apply this in your convolution, even when you are doing padding and packing, you might need to apply this. So you just take note of that. Talking about stride, I think you've covered this in your class lectures, but just to reiterate, it's important to know what stride can do to your input and your expected output. So if you're using a stride of 1, you'll probably be increasing the output that you get from a particular input. If you're using a lower stride, it's like you're doing max pooling. So you will be shrinking out that input to a lower dimension. So having a stride greater than 1 reduces your computation for LSTM, because so when you're doing striding, you are scanning over. So when you decide to maybe skip so many number of time steps before doing your scanning, that will decrease. You obviously have like less number of scannings to do. So if you have a whole sequence that you need to scan through, and your stride is greater than 1, you will skip so many time steps before you go to the scanning, before scanning the next time step. So that will be computationally like easier or faster when it comes to LSTM. But also take note, like too much of striding will make your model not to explore more of your input, and you might not have enough. So you can just take note of that when you're doing your homework. So as I said, stride greater than 1 alters the number of time steps, and you might also change the length accordingly. So we've given you, I think, in your lecture slides, how you can calculate like your given a particular stride and kernel size, how you can calculate the change in the length or your output that you have. One more thing about the embedding layer, you've done like building models in your homework 2, exploring different type of models. say ResNet, ConvNext, and all of that, which basically like they were used for feature extraction for your image processing or face recognition that you did. But this time around, you can also try something like that for uh, uh, your embedding layer. So the idea is extracting more information from your input. So you can use like a deeper model, but this might be using a like this will be like you're using a very large model to solve a problem that maybe could also be solved with like 1D convolution or 2 layers or 3 layers of embedding layer. So now leave Shobab to continue.
So now we'll begin the sequence model, which is inside the encoder. And you are free to use the RNN, the GRO, but we mostly recommend you to use the LSTM from the torch.nn, which expects the packed padded sequence method. You can check from the documentation. The important parameters we have the input size, the hidden dimension, the number of layers, dropout, bidirectional. Kindly note that where bidirection is true, LSTM has an output shape of hidden dimension, and note that the total output dimension is 2 into hidden dimension. The PB LSTM, it is described in this paper, which is bidirectional LSTM variant of up by LSTMs, which downsamples by a factor of 2, basically concatenating adjacent pairs of input. And you can implement this by using the reshape. This is a figure which explains you how the downsampling and bi-LSTM works. Notice the dimension is 2 into hidden since the LSTM is bidirectional. We have provided you with the pseudocode of the PB-LSTM. You can go over, we'll put this on the website. Now we'll go to the classification layer, which is a part of the decoder. The classification layer is just same as the homework 1 part 2 and MLP. Its output goes from the sequence model to the classification layer. You can see this. The sequence model outputs go to the classification layer. And you can have a experiment of all variations, make it a deeper, wider, try different activation layers, try a dropout. And for the hyperparameters, you can try the Capstral normalization, different weight initialization, weight decay with optimizer, and reduce LR on plateau. Most of our ablations are based on this, and Levenstein distance might start to oscillate at lower values, to kindly be wary of that. You can also use the step LR. For the optimizer, you can use the Adam W and start the learning rate with a small value. Now you have to use the dropout in 3 layers, the embedding, sequence, and the classification. You can start with a small value and increase as the model gets trained. You have to also use the log dropout for the LSTM. It has to apply the same dropout mask to every time step. You can refer to the PyTorch NLP. And here is a visualization of time masking and time frequency. The time masking is vertically masking it, as you see in the left hand side, bottom of the visualization. And the frequency masking is the horizontal masking in the right hand bottom visualization. Now, the beam width, start with a high beam width, can give you better results. Even a beam width of 1 for the greedy search also gives good results. Also, don't use a high beam width. for validating in each type of epoch. And final tips, split your work among your team as you've been doing. If you're not doing, start doing. Try a different ablation with every team member. And we have a lab 9, which is due on the 14th of March, which will be going deeper into the CTC and beam search, and do attend that. Finally, good luck with that. Thank you.